Okay, so today we're going to be solving problem 2.18, which says two spheres, each of radius r, and carrying uniform volume charge densities plus rho and minus rho respectively, are placed so that they partially overlap as shown in the figure below. Call the vector from the positive center to the negative center, d, and show that the field in the region of overlap is constant and find its value. Then the problem gives the hint, use the answer to problem 2.12. Problem 2.12 was essentially finding the electric field inside of a solid sphere with uniform volume charge density, so we'll go ahead and start with that. But first, to review, Gauss's law says that the electric flux through the area of a Gaussian surface is equal to the charge enclosed by that surface divided by epsilon naught. So you've got two parts of the equation here, which we'll find separately and then put them together to find the electric field. So first, to start with the single sphere, we start with a sphere with big radius r, and we want to know the electric field in this sphere. So we can draw our Gaussian surface inside that sphere. It's specifically a Gaussian sphere. Oh, that's a poor drawing. And we'll say that this has radius little r. So starting with the left half of Gauss's equation, or Gauss's law rather, we want to find this differential area element. And, this makes sense because it's a sphere and it has a fixed radius r. We can say our differential area element is going to be equal to r squared sine theta d theta d phi. And this is because only theta and only phi are changing. R is constant. And this is pointing in the r hat direction because it's a vector. All right, so another important thing to note is, how much theta and phi are changing. If we draw just a little sphere over here, we want to integrate over the entire sphere. So theta, which is this angle here, is going to go from 0 to pi, right? And then phi, which is the angle that sweeps around the circumference of this sphere, will go from 0 to 2 pi to encompass the entire sphere of radius r. Cool. So we can say theta goes from 0 to pi, and phi goes from 0 to 2 pi. Great. So now the other part of this is recognizing the electric field. Now, we're trying to solve for the electric field, and so we can just say that it's some magnitude, but what direction does it go in? To think about this, let's think of a charged sphere like this. Actually, yeah, let's think about this sphere over here with big R, right? Radius big R. So if we want to figure out what direction our electric field is in, we can draw another, actually, let me change the color. We can draw another Gaussian surface around the outside and kind of take a look. Now, here's one way to think of it is if you take a section of this sphere right here, and you look at the charges, or if you look at the electric field that comes from that, it'll look something like this. So you'll have differential element of the electric field going this way, differential element of the electric field going this way, and an element going this way. Now, right away, it should be pretty obvious that the horizontal components of both this vector and this vector will cancel, which leaves only this component pointing outwards. And that can work, you know, if you use this little subsection here, that'll be the same case up here. And so from that, we can basically, because of the spherical symmetry, we can conclude that the electric field is going to be in the r hat direction. So to come back here, we can just say that E vector can just say is the magnitude of the electric field in the r hat direction. And then we're going to find what this is. Cool. So now to actually evaluate the integral, so E dot dA is going to be equal to ER squared sine theta d theta d phi. And we can say for sure that these are constant. So now putting it in the integral with our bounds, that'll be, actually I'll just go ahead and pull the constants out. Times the integral from 0 to pi sine theta d theta times the integral from 0 to 2 pi of d phi. Now, the integral from 0 to 2 pi of d phi, well, that's just going to give you phi evaluated from 0 to 2 pi, which will just give you 2 pi. That one's pretty easy. So then we can just say this is equal to 2 pi. Now, the integral of sine theta from 0 to pi, well, let's see. We know that the integral of sine theta is going to be negative cosine theta, and it's evaluated from 0 to pi. So, the negative cosine of pi is going to be negative times negative 1, because cosine of pi is negative 1, minus the negative cosine of 0, which is 1. And this gives us 2, which is, you know, nice answer. So then we can say that this whole part here gives us 2. So our final answer for the left part of Gauss's law will give us 4 pi r squared times magnitude of the electric field. And this makes sense because 4 pi r squared is the surface area of a sphere. So now for the right side, which is the Q enclosed over epsilon naught. So with this whole sphere, because it does have a uniform volume charge density, we can say that it has a total charge, Q, equal to the charge density times the volume. Cool. So we can say that Q enclosed is equal to the charge density times the volume of our Gaussian sphere, which will be 4/3 pi little r cubed. And it asks for Q enclosed over epsilon naught, and because that's a constant, we can just go ahead and throw that in there. So now we have the left and right half of our Gauss's law equation, so we can now solve for what our electric field is. So E, the magnitude of the electric field, times 4 pi r squared is equal to rho over epsilon naught. I drew that incorrectly. Times 4/3 pi r cubed. Now looking at this, right away we can say the 4 pi's cancel, r squared cancel, leaving just one r on the right side, which means that our electric field inside this sphere of uniform charge density is E equals rho r over 3 epsilon naught. And because it is a vector, you can say that it's pointing in the r hat direction, as we found earlier. Now, there is a small simplification that I can make that'll make more sense later, and that is to say that r hat is equal to r vector. So we can rewrite our electric field rho over 3 epsilon naught r vector. Boom. There we go. Okay, so now moving on to the actual example at hand, we have two overlapping spheres, one with the charge density plus rho, one with charge density minus rho. And the problem says that the distance from one center to the other is this vector d. Now what we want to know is we want to know the electric field at some point P in this overlapping region. So, a convenient way to do that using our example or using our answer from the previous problem is just use two Gaussian spheres. Because in this case, here, if I draw, this is a poor sphere, if I draw this Gaussian sphere, and I do another one for the opposite sphere, this is great because both Gaussian spheres are still inside their original sphere, so our answer from the previous problem still holds. However, because it includes that center point, it allows us to find the electric field at that point. So, also it's important to note that with this, with these Gaussian spheres, you'll have your, electric field still pointing, radially outward. And the simplification that I made earlier, or we'll say that this is DE. And the simplification that I made earlier is saying that it is in the r vector direction. We can say that for this left sphere, the full electric field is E, we'll call it E plus. E plus is equal to rho over 3 epsilon naught in the r plus vector, or times the r plus vector. And that r plus vector, we'll draw there. And then the electric field from the second sphere will be pretty much the same, but opposite. Minus is equal to minus rho over 3 epsilon naught in the r minus vector direction. We'll draw that going this way. Now, because we can use the principle of superposition with electric fields, we can say that the total electric field is equal to E plus vector, E minus vector, which is equal to rho over 3 epsilon naught like that. Now, of course, this can be simplified by factoring out the constants. We'll just say and this E total is for this point in that region. Actually, you know what? Just for clarity, I'm not going to call this E total. I'm just going to call that plain. There we go. Times R plus vector minus R minus vector. All right, now there's another simplification that can be made here that might not be super obvious. So if we draw what's going on inside our sphere without the spheres, so we've got the vector D, and we've got our point P, and then we've got the R plus vector and the R minus vector. What we can see looking at this is that R plus vector minus R minus vector is equal to that D vector. Actually, yeah, these should be labeled with a vector to be correct. Yeah, so then our electric field at any point here in this overlapping region can be reduced to rho over 3 epsilon naught times that, oh, it's a bad D, that D vector. And there we go. That is proving that the electric field in this region is constant, and that is its value by Gauss's law. Thanks so much.